we have already studied the advantage of differential pulse code modulation over pulse code modulation. In differential pulse code modulation, the difference between consecutive sample is being, that is input to the 1 bit quantizer, but in case of pulse code modulation the whole sample is input to the quantizer, and the noise power is, the power of noise, this is MP square by 3L square. Now, if we will give input, if we will give difference of consecutive sample as input, the maximum value of MP will be, the value of MP will be lesser. So, in case of DPCM, differential pulse code modulation, the noise power will be less. The noise power is lesser in case of DPCM. Now, after studying advantage of differential pulse code modulation, I have drawn the block diagram for delta modulation scheme. This block diagram is not the actual block diagram as we study in the books, but this block diagram is better to understand and better to explain. So, to understand this block diagram and working of delta modulation, first we will study 1 bit quantizer. In pulse code modulation, we may have 2 bit, 3 bit or n bit quantizer, or we may have different bit quantizer depending upon quality of transmission. If we want better quality, the number of bit in the quantizer should be high. So, if we have 2 bit quantizer, we will have 4 levels. The number of level is equal to 2 to power n. But in case of delta modulation, to understand the working of this block diagram or delta modulator, first we will study the working of 1 bit quantizer. If it is a 1 bit quantizer, the number of level is equal to 2 to power n. If n is equal to 1, we will have 2 levels, L equal to 2. 0, if the signal is greater than 0, this will come under first level, and if the signal is less than 0, this will come under the next level, and 0 will be the boundary of 2 level. So, we will have only 2 output of quantizer. If the input to quantizer is greater than 0, the output of quantizer will be this dotted line, the positive dotted line, and if the input to quantizer is less than 0, we will have negative dotted line. So, there are only 2 possible set of the output of quantizer. The positive value is called positive threshold, and this is negative threshold. In delta modulation, the positive threshold is, or the positive output is represented by plus E, and this is minus E. So, the output of quantizer is plus E or minus E. The plus E will be encoded with 1 and minus E will be encoded with 0 and then transmitted. This is receiver end. We have already studied quantization in detail in the while we studied quantization. So, I do not think you will have problem in understanding 1 bit quantizer, because in quantization we have studied 3 bit quantizer. So, it will have 8 level quantizer. So, this is very easy. Okay. Now, we will study this block diagram. This is receiver end. So, depending upon plus E and minus E, 1 or 0 will be transmitted, and here we will have decoder. So, corresponding to plus 1, the output of decoder will be plus E, and corresponding to 0, the output will be minus E. So, equivalently we can say that plus E or minus E will be received at the receiver end. So, if I erase this, we will have plus E or minus E is being transmitted, and plus E and minus E is being received. So, I have removed encoder and decoder here. I have not showed encoder and decoder. We will understand the meaning of what does this block diagram do. So, to understand this, I am making it separately, or plus E will be received. So, instead of representing plus E or minus E, I am representing the sequence of input. This may be input may be xk. I am representing plus E or minus E by general value xk. This may be x1, x2, x3, and here it is yk. This is delay by 1. So, here we will have yk minus 1, and yk minus 1 is being added to the sequence of input. This is also positive. So, from this summation we can write it as xk plus yk minus 1 is equal to yk. Here if we put x equal to k, if we put k equal to 1, we will get x1 plus, or this can be written as yk minus 1 is equal to xk. Now, if we put k equal to 1, we will get y1 minus y0 is equal to x1. If we put k equal to 2, we will get y2 minus y1 equal to x2. So, here we will have y2 minus y1 is equal to x2. Similarly, if we put k equal to 3, we will get y3 minus y2 is equal to x3 dot dot dot. If we put k equal to k, we will get yk minus 1 equal to xk. Now, if we add all these equations, y1 and y1 will be cancelled, x0 will be cancelled by its previous equation. Similarly, x2 will be cancelled with y2 will be cancelled by this y2, y3 will be cancelled by this y3. So, on the left hand side we will have only yk is equal to, on the right hand side we will have summation of all the input sequence, or we can write it as yk is equal to summation of xm, where m is equal to 1 to k, or output is equal to summation of input sequence. So, here we will have output is nothing but summation of all the input sequence. And what is the input sequence? There are only two types of input. Either it is input at the receiver, and this input is nothing but this is output of quantizer, and this can be either plus E or minus E. So, output is nothing but this is summation of plus E or minus E. So, here we can write as the output of receiver. The output of receiver is equal to summation of plus E or minus E. And when we will get plus E or minus E, if the input to quantizer is positive, since this is 1 bit quantizer, so the output can be, there are only 2 levels, and corresponding to 2 levels there will be only 2 outputs, possible outputs. So, it will be plus E or minus E. So, if the input to quantizer is positive, the output of quantizer will be plus E, fixed level. The positive value may vary, but for corresponding to all the positive value, the output of quantizer will be plus E, and corresponding to all the negative value, we will get same minus E value. So, this is the meaning of quantizer. So, similarly, the output will be summation of all the positive threshold or negative threshold. So, suppose first we are getting, if we try to draw a graph, suppose initial output is 0 and first we are getting plus E. Suppose here the input is positive, we will get plus E. So, the first y1 will be the first input, this will be plus E. Again suppose here the value is positive, then again plus E will be added, again suppose it is positive, then at next instant suppose here the input is negative, we will get minus E. So, minus E will be again added to the output. So, we will get this type of output sequence. At each step either plus E or minus E will be added to the output. Output at instant y3 is equal to output at y2 plus the input. So, we have understood the meaning of 1-bit quantizer and receiver. Receiver is at the receiver, output is nothing but summation of plus E or minus E. So, now we will take an example. We will take a sinusoidal signal and we will try to transmit the sinusoidal signal with the help of this block diagram or with the help of delta module. Instead of drawing block for receiver end, I am just writing it as at receiver output will be summation of plus E or minus E. Suppose the sinusoidal signal has a frequency of 1 kilohertz. For transmitting it, we will first digitalize this signal. So, we will do sampling of this signal, and suppose the sampling frequency is 10 kilohertz. The sampling frequency is 10 times higher than the frequency of analog signal. So, in the one time period of original signal, the time period of the sampler, for sampling we will multiply it by impulses. So, the frequency of impulses is 10 kilohertz. So, we can say that in one cycle of analog signal there will be 10 cycle of impulses, or in one cycle of analog signal there will be 10 impulses, and for sampling we have to multiply analog signal with the samples. So, equivalently we can say that in one cycle of analog signal we will have 10 samples of analog signal, because 10 impulses are present. So, instead of drawing impulses in this graph, I am drawing the samples of the original signal. So, in one time period or one cycle there are 10 samples of original signal. So, in half cycle there will be 5 samples of original signal. Suppose this is first sample, this is second, third, fourth and fifth sample. This is first sample, and suppose the signal is A sin omega t, or suppose A equal to 1 millivolt. So, the signal is sin omega t millivolt, and it is divided in 5 parts. So, this angle will be 36 degree, this is 72 degree, this is 108, 144 and 180 degree. So, here the sample value will be, this is the first sample, this will be sin 36 degree. Sin 36 degree is equal to 0.587. The second sample will be sin 72 degree. This is 0.951. Third sample will be sin 108 degree. Sin 108 is equal to 0.951. The next sample will be sin 144. This is 0.87, and last sample is 0. This is sin 144 and this is sin 180. So these are the samples, and we have to transmit these samples. Now in pulse code modulation, this sample is input to the quantizer and the output of quantizer is corresponding to this sample. But in this case, in case of differential pulse code modulation, instead of giving this input to the quantizer, we will input difference between this input and estimated value of previous input. Suppose this is the input, the actual value of previous input will be 0, but in the block diagram we do not have the actual value of previous input. So I have written it here, estimated value of previous input. Here we have sequence of actual input. So the first input is sin 36 degree. So first sin 36 degree will come here, then sin 72 degree, then sin 108, sin 144, and then sin 180 degree. This sample will be, these are the input. Here we have estimated value of previous input. The actual value of previous input is 0, but we do not have actual input. So suppose the estimated value of previous input is not exactly 0. Suppose the estimated value of previous input is 0.1. So the first input to the quantizer will be the difference between sin 36 degree and 0.1. So sin 36 degree is 0.587. So the first input to the quantizer will be 0.487 millivolt. Now the output of quantizer is either plus E, plus threshold, or minus threshold. So suppose the value of E is set to suppose this is set to 0.3 millivolt, and suppose initial output is 0, yk is equal to yk minus 1 plus xk. And what is xk here is, xk from the block diagram of receiver we can write yk is equal to yk minus 1 plus xk, and xk is nothing but the transmitted signal. Xk is either plus E or minus E. So the first input to the 1-bit quantizer is 0.87. Since it is positive, so the first output of quantizer will be 0.3 millivolt. And suppose initially yk minus 1 is equal to 0. So at k equal to 1, this is y0 plus x1. So the x is the output of quantizer. So y1 will be, y0 is 0 plus the output of quantizer is plus A. This is 0.3. So y1 will be 0.3 millivolt. Here I am plotting output at receiver. Output at receiver. Or suppose in the same graph I am plotting output. Suppose the original signal is, I am plotting it as dotted line. And in the same graph I am plotting output at receiver. So the first output is at k equal to 1, here k is equal to 1, here k is equal to 2, k is equal to 3, k is equal to 4, and here we have k is equal to 5. So, at k equal to 1, the output is 0.3 millivolt. This is 0.587 millivolt. So, the 3 millivolt will be like this. So, this is the first output. At k equal to 2, now this signal has been transmitted. Now, sin 72 degree will come, and this is the estimated value of previous input. This is equal to, this is nothing but output delayed by 1. So, if k is equal to 2, we will say that sin 72 degree is equal to second input, k is equal to 2 here. So, here we will have output delayed by 1. So, if k is equal to 2, here we will have y 1, and value of y 1 is equal to 0.3 millivolt. So, now here we have y 1, that is 0.3 millivolt, and the next input is sin 72 degree. So, sin 72 degree is 0.951, and this is 0.3 millivolt. So, the input will be, input to the quantizer will be 0.951 minus 0.3. So, this will be 0.651. Again the input to quantizer is positive. So, the output will be plus E. Now, again y 2 will be, the second output will be y 1 plus x 2. X 2 is again positive, this is 0.3, and y 1 is equal to 0.3. So, next output we will get as 0.6 millivolt. So, the next output will be 0.3 plus 0.3, 0.6 millivolt. So, this has been transmitted. Now, the next input is sin 108. Value of sin 108 is 0.951, and this is input at k is equal to 3. Now, here we will have output delayed by 1. So, if k is equal to 3, here we will have y 2, output at k is equal to 2, and output at k is equal to 2 is 0.6 millivolt. So, this will be 0.6 millivolt. Now, at this instant 0.951 and 0.6 millivolt will be compared. So, here the signal will be 0.351. Again the input to quantizer is positive. So, output will be 0.3 millivolt. So, we will write it as y 3 is equal to y 2 plus x 3. X 3 is again positive, y 2 is equal to 0.6, and x 3 is positive threshold. So, this will be 0.3. This is 0.9 millivolt. This is 0.951, and at k equal to 3, the output we will get it as 0.9 millivolt. So, these are the outputs. Similarly, this has been transmitted. Now, the next input sequence is sin 144. Sin 144 is equal to, now k is equal to 4, and sin 144 is equal to 0.587. So, 0.587 is lined up, and k is equal to 4. Here we will have output delayed by 1. So, the output will be y 3, and y 3 is equal to 0.3, 0.3, 0.3. This is 0.9. So, output at k is equal to 4 will be y4 is equal to y3 plus x4. What will be x4? The input at k equal to 4 is 0.587 and here output delayed by 1. So, here the signal will be 0.9. Now, the difference is negative 0.587 minus 0.9. So, here the signal will be negative, and if any negative signal is input to the 1 bit quantizer, the output will be minus threshold value. So, here we will get x4 as minus 0.3 millivolt. So, y4 will be y3 is equal to 0.9 minus 0.3, 0.6 millivolt. So, now the output will be, this is 0.587 level and this is 0.6. So, if we will subtract 0.3 from 0.9, we will get 0.6 millivolt. This is the level of 0.6 millivolt. This is also 0.3 and this is also 0.3, although it looks like shorter than 0.3. This is also 0.3 and this height is also 0.3, although I couldn't make it equal. Okay. So, the next input sequence is sine 180 at k equal to 5. At k equal to 5, the input is 0 here, and here we will have y4, and value of y4 is 0.6 millivolt. So, again the input to quantizer is negative. So, we will get output as 0.3 volt. So, similarly, now we will subtract 0.3 millivolt. So, the output we will get it as 0.6 minus 0.3, 0.3 millivolt. Again at this point, the next input is will be this sequence. This is minus 0.587, this is minus 0.587. So, here we will have minus 0.587 and output delayed by the previous output is, this is 0.3. So, here we will have 0.3. So, minus 0.587 minus 0.3 will be negative. So, the output of quantizer will be minus 0.3 millivolt. So, at next instant we will again subtract output by 0.3 millivolt. Now, at this point output is 0 and the next input is 0.951. The next input is 0.951 minus 0.951 and here the signal will be 0. Now, again input to quantizer is negative. So, the output will again be subtracted by 0.3 millivolt. So, what we are doing here, at each instant we are comparing the present sample, the present input sample and previous output, and if the difference is positive, we will add the threshold to the present output, and if the difference is negative, we will subtract the threshold from the output. So, if we compare at this point, this is the next input sequence, this is minus 0.951 and at this point the output is minus 0.3, minus 0.951 and minus 0.3. So, to draw the output, what we will do, suppose we want output at this instant, this is some value of k. What we will do, we will subtract the previous output. Suppose the previous output is this level, this is the level of previous output. So, we will subtract the previous output from the present input. The present input is minus 0.951 and the previous output is 0 level, and if we will subtract, we will get negative value. So, the negative value will be the input for 1 bit quantizer, and if negative value is input for 1 bit quantizer, the output of quantizer will be negative threshold. So, the negative threshold will be added to the present output. So, the present output will be 0 minus 0.3 millivolt. This is negative 0.3 millivolt. Again at this point, this is the next input. If we want output at this instant, the input is again minus 0.951 and output at this instant is, the previous instant is, this is the previous output, this is minus 0.3. So, minus 0.951 minus 0.3, again negative value. So, we will again subtract 0.3 from the output. If you want output at this instant, the input at this instant is minus 0.87, minus 0.587, and the output at previous instant is minus 0.6. Now, if you subtract minus 0.6 from minus 0.587, you will get a positive value. So, if you will get positive value here, the output will be, we will add 0.3 to the output. So, now the output will be plus 0.3 will be added to minus 0.6. So, we will get this output. Here the input is 0 and the previous input is, the previous output is minus 0.3. So, again input to quantizer will be positive value. So, again this will be 0.3 will be added to the output. So, this way, now if we compare the original signal, this is the original signal. This is the original signal, the dotted line is original signal, and the output that we will receive at the receiver end is drawn by the blue color. So, we can see here the error is significant. The output is not tracking the input very accurately. Now, if you want the output to track the input very accurately, now if we increase the sampling frequency, instead of taking 5 samples in one half cycle, if we take 10 samples, so the difference between, so it will, if the number of samples are more in one half cycle, there will be more tracking options. Here in one half cycle we have 5 tracking options. If there will be, if the sampling frequency is high, we will have option, the tracking will be more accurately. So, overall this is what we will do to find out output of delta modulator. At each instant of k, we will compare present input and the previous output. That is, if I represent the present input by mk and previous output at kth instant, the previous output will be yk minus 1. So, at each instant we will compare mk and yk minus 1, and if mk is, if input is greater than the previous output, the input to the quantizer will be positive, and if input to the quantizer is positive, the output of quantizer will be plus E. So, if the present value of input is greater than the previous value of output, we will add E to the previous output, and if mk is, if the present input is less than the past output, the output will be subtracted. So, based on this, I will take another example, a different value of E in the same input. Now, I will take E is equal to 0.5 millivolt, and we will again draw it. If we will do one more problem after doing the another example, this will become very easy for you. Suppose initially output is 0, we will write y1 is equal to y0 plus, here we have plus E plus 0.5 millivolt or minus 0.5 millivolt. In the block diagram of receiver, I have written yk is equal to yk minus 1 plus xk. Now, we have to compare. Initial output is 0. I will draw the output with blue sketch. So, suppose initial output is 0. Now, suppose this instant is for k is equal to 1, because this is the first sample. This instant is for k equal to 1, this is for k equal to 2, this is for k equal to 3, this is for k equal to 4, this is for k equal to 5, this is for k equal to 6, k equal to 7, k equal to 8, k equal to 9, k equal to 10. So, if we want output at k equal to 1, we will compare. If k is equal to 1, we will compare m1 and y0. y0 is equal to 0 and m1 is the first sample. The value, the m1 is, the value of m1 is, we will compare m1 and y0, the present input sample and the previous output. m1 is for k equal to 1, this is 0.587 and y0 is equal to 0. So, here m1 is, mk is greater than yk minus 1. So, here 0.5 will be added to the output. So, at k equal to 1, the output will be 0 plus 0.5. So, here the output will be 0.5 millivolt. Suppose this is 1 millivolt level, this is 0.5, 1 millivolt level, this is 0.5 millivolt level. So, at k equal to 1, we have output is equal to 0.5 millivolt, 0.5 millivolt. Now, for k equal to 2, we will compare m2, the next input sample, and y at 1. Y at 1 is equal to, this is 0.5 millivolt, and m2 is sine 72 degree, this is 0.951. So, m2 is greater than y1. So, we will add 0.5 millivolt, we will add threshold to the output. So, the output will be, at k equal to 2, the output will be 0.5 plus 0.5, 1 millivolt. Next, to obtain output at k equal to 3, we will compare M3 and Y2. M3 is 0.951 and Y2 is 1 millivolt. Now in this Mk is less than Yk minus 1, M3 is less than Y2, so we will subtract the threshold from the output. So at k equal to 3, the output will be subtracted. So from k equal to 2 to k equal to 3, the output will be constant, and here we will subtract 0.5 millivolt. To obtain output at k equal to 4, this is k equal to 4. So at k equal to 4, we will compare M4 and Y3. M4 is equal to the input sequence at k equal to 4. So input sequence at k equal to 4 is 0.587. This is 0.587, and Y3 is equal to 0.5. So now Mk is greater than Yk minus 1. So we will add 0.5 to the previous output. So at k equal to 4, 0.5 will be added. So this will be the output. So Y4 is equal to, this is Y3, Y4 is equal to now 1. To obtain output at k equal to 5, we will compare M5. So M5 is 0. This is 0. So the present input is less than previous output. So we will now subtract. So Y5 will be 1 minus 0.5. So this will be 0.5. So here the output will be 0.5. This is the output. These are the outputs. Now to obtain output at k equal to 6, this is k equal to 6, we will compare M6 and the previous output M5. Now M6 is, this is M6 minus 0.87, minus 0.587. So the input is less than previous output, so we will subtract output here. So at k equal to 6, at this instant we will subtract 0.5. So this will be the output. So Y6 is equal to 0. To obtain output at k equal to 7, we will compare M7 and Y6. M7 is minus 951. So again previous output is greater than, so again we will subtract. So at k equal to 7, Y7 is equal to minus 0.5. To obtain output at k equal to 8, we will compare it with M8. Now M8 is equal to, at k equal to 8, output is, input sequence is minus 0.951. So again input is less than previous output, so the output will be subtracted. So Y8 will be, now Y8 will become minus minus 1. Y8 is equal to minus 1. So at k equal to 8, the output will be subtracted, and this is minus. To obtain Y9, we will compare M9 and Y8. M9 is at k equal to 9, the input is minus 0.587 and output is the previous output Y8 is equal to minus 1 so and M9 equal to minus 0.587. So the input is greater than the output, so 0.5 will be added to the output. So this will be the output at k equal to 10. So Y9 is equal to minus 0.5, this is minus 0.5. To obtain Y10, we will compare M10 and Y9. M10 equal to 0 and Y9 equal to M10 is equal to 0 and Y9 is equal to minus 0.5. So the input is greater than previous output, so output will be 0.5 will be added to the output. So Y10 will be equal to 0. So at this point we will have output is equal to 0. So these are the outputs obtained by delta modulator. These are the outputs obtained by delta modulator. And the actual input is, now in the same graph we will draw the actual input that has to be the actual signal that has to be that was to be transmitted, and we will compare it. The actual signal is like this. This is the actual signal. So now if we compare the actual signal and the signal, the dots, these are obtained by delta modulator. Now in this case error is somewhat reduced as compared to the previous case. In previous case we had chosen threshold E is equal to 0.3 millivolt. So to minimize the error, the threshold is properly chosen. So in this case the error is reduced. Now if we will take very high value of threshold, suppose we take E is equal to 1.5 millivolt, and you try to draw with the same procedure. Now the procedure has become very simple. You just have to compare the present input and the previous output, and if present input is greater than previous output, the threshold will be added to the previous output to obtain the present output. So with the same procedure, now if you take very high value of threshold and you compare the original signal and the signal obtained by delta modulator, in this case you will find the variation will be very high. So the value of threshold is chosen very properly. Here the sampling frequency I have taken 10 times more than the original signal, but if you want to reduce the error, if you increase the sampling frequency, the tracking will be dense. I mean, in 1/2 cycle there are 5 options to track. If we double the frequency in 1/2 cycle, we will have 10 options to track. So if the tracking is dense, if the sampling frequency is high, the tracking will be dense. In that case error will be reduced, but in drawing I cannot increase the frequency because the drawing will be very difficult. For E equal to 1.5 millivolt, I am giving you to draw it, and you will see the error will be very high. In the next case, I am taking very low value of threshold. If I take 0.1 millivolt, as the value of threshold, and in this case again I am trying to draw the output. When you will put E is equal to 1.5 millivolt, you will find the tracking will be very poor. So, you can say that there must be an upper limit for the threshold. So, upper limit is defined, there is also a lower limit. So, first I am keeping very low value of threshold, and we will see what is the problem, and then we will define the lower limit. So, in the next case I am taking the very low value of threshold, that is 0.1 millivolt. We have done for 0.3, 0.5, you will do for 1.5 millivolt, and I am doing again for 0.1 millivolt, a low value of threshold. So, I am drawing it, and then we will see what is the problem in tracking. E is 0.1 millivolt. We have to obtain, suppose y0 is equal to 0, we have to obtain y1, y2. To draw the waveform for threshold of 0.1 millivolt, we have yk equal to yk minus 1 plus xk, where xk is, this is output of quantizer, and values of xk may be, this may be plus minus a, depending upon the estimated value of previous output is greater than the present input or not. So, I have listed down the different outputs, and here I am listing inputs. The first input is M1, second is after M1 M2 and M10 M11. So far we have concluded that after studying the theory of quantization, so far we have concluded that if present value of input is greater than the estimated value of previous output, estimated value of previous output, which is also equal to, if mk is, if the present input is greater than estimated value of previous output or simply previous output, we will say if mk is greater than yk minus 1. So, after studying theory of delta modulation, we have concluded that if present input is greater than previous output, the present output will be yk is equal to the threshold, the positive threshold will be added to the previous output, and if mk, if the previous input, if the present input is less than the previous output, we will subtract the threshold from the output. Minus E. So, suppose k is equal to 1, then the present output will be M1 and the previous output will be M0. So, for k equal to 1, here we have k equal to 1, this is k equal to 1. This is k, this is k minus 1, and again here we have k. So, here we will have y1. So, for k equal to 1, M1 the present input is greater than previous output, because the previous output I have taken as 0. I have assumed to start it, I have assumed the previous output as 0. So, M1 is equal to sine 36 degree, this is 0.587. So, the present output is greater than previous output. So, in the previous output a threshold will be added. So, y 1 will be equal to y 0 plus E, and we have E is equal to 0.1 millivolt. So, y 1 will become 0.1 millivolt. We will make y 1, here we will plot y 0 is equal to 0, here we have this line is for k equal to 1. So, y 1 will be 0.1 millivolt. I am taking threshold, I have taken very low value of threshold, and we will observe what is the problem if we will take very low value of threshold. So, this much height is 0.587, approximately 0.6. So, I am taking 0. This length as 0.1. So, y 1 equal to this. Now, to obtain y 2, or for value of k, the present for k equal to 2, present input is m 2 and the previous output will be y 1. So, we will compare m 2 and y 1. The value of m 2 is sine 72 degree, which is 0.951, m 1 is equal to 0.587, this is 0.951, m 3 is equal to 0.951, this is 0.587, this is 0, this is k equal to 2, this is k equal to 3, this is k equal to 4, this is k equal to 5, okay. So, I have listed all the values of present input and all the values of, and we are trying to find out all the values of output and previous output. So, for this is k equal to 1, this is k equal to 2, this is k equal to 3, k equal to okay. So, for k equal to 2, present input is m 2 and past output is, previous output is 0.1. So, if we will compare it, the next output will be, the present output will be, since present input is greater than previous output, so we will add 0.1. So, this will become 0.2. So, at this is k equal to 1, at k equal to 2, the output will become 0.1 plus 0.1, 0.2. So, this is the output at k equal to 2, this is output at k equal to 1. Again, if we compare, the present input is greater than previous output. So, this will be 0.2 plus 0.1, 0.3. So, at k equal to So, at k equal to 2, to find out y 2, we will compare m 2 and y 1, and since m 2, the present input is greater than the previous output. So, y 2 will be 0.1 plus 0.1, this is equal to 0.2. So, we have here 2. Now, y 2 is equal to 0.2. Again, we will compare present input and previous output, since we are at k equal to 3. So, if we compare it, the present input is greater than the previous output. So, the next output y 3 will be equal to the previous output plus 0.1, this is 0.3. So, at k equal to 3, we will have 0.3 as output. Next, to find out y 4, we will compare y3 and m4. y3 is equal to 0.3 and m4 is equal to 0.581. So, again we will add 0.3 plus 0.1, this is 0.4. To find out y5, we will compare m5, the present input at k equal to 5, and the previous output y4. Now, m5 is 0 and y4 is equal to 0.4. At this point, the previous output is greater than the present input. So, we will subtract the threshold from the previous output. So, y5 will be 0.4 minus 1, this is 0.3. So, at k equal to 5, we will subtract 0.1. So, this is the output at k equal to 5. To find out y6, we will compare m6, this is minus 0.587 and this is positive. So, here also input is less than the previous output. So, the next output will be 0.3 and here we will subtract 0.1. 0.2. So, now we will try to make it in the graph only. At k equal to 6, we will compare it with, to find out output at k equal to 7, we will compare y6 and m7. So, m7 is minus 0.951, this value is minus 0.951 and this is positive. So, the input is less than previous output. So, at this point we will subtract 0.1. Again the next input is less than. So, again we will subtract, this is 0.1, this is 0.2, this is 0.3, this is 0.4, this is 0.3, this is 0.2, this is 0.1. So, at this point this will become 0. Now, to obtain output at k equal to 9, we will compare m9 and y8. So, the input is again less than the previous output. So, it will again decrease by 0.1. So, this is the output at k equal to 9. Here output is negative and the next input is 0. So, at this point we will add 0.1. So, this way we can plot the output comparing present input and previous output. So, now you can see it, the mismatch between the actual output, the actual signal and the output of delta modulator if the threshold is below, that is 0.1 millivolt. If you plot it at this value, here we have value m3, this is. Now, if we plot the actual output, now if we compare the expected output, the desired output with the output of delta modulator, at 36 degree we have 0.587, this should be the actual output. Here we should have 0.951, here also 0.951, here we should have here we should have 0.587 and here we should have, at this point we should have 0. So, if we plot the desired output, this is the desired output and this is the output of delta modulator. So, here we can say the output of delta modulator is very slow as compare of input. If you will draw the same output taking E is equal to 1.5 millivolt, in this case also the tracking will be very poor, but in this case you will observe that the change in the output of delta modulator is very fast as compared to the input, but here the change in the output of delta modulator is very slow as compared to the input. So, if we compare input with the output of delta modulator, we can say that the slope of input is very high. So, this problem is called slope overload. The slope of input is very high as compared to the rate of change of output of delta modulator. This problem is called slope overload. This is slope overload. Now, so if we want to solve the problem of overload, we will have to increase the value of threshold. So, when you will plot taking E is equal to 1.5 millivolt, the tracking will be poor. So, you can say that the upper limit of threshold is defined. We should not have very high value of threshold. So, upper limit is defined. Here we have taken very low value and we have a problem. So, we will say lower limit is defined to have an optimum value of threshold for which the tracking will be sufficiently accurate. Now, to avoid slope overload, suppose what is happening here, the previous output is 0, this is the y 0, and the desired output is 0.587, but we got a change of 0.1 millivolt. If you will take threshold equal to 1.5 millivolt, here the desired output is 0.587 millivolt, we are getting 0.1 millivolt, and if you will take E is equal to 1.5 millivolt, the output will be 1.5 millivolt. This will be even bigger mismatch. So, we need to, so we will keep E is equal to around 0.6 millivolt or equal to 0.5 millivolt. And to avoid slope overload, since in case of slope overload the threshold is very less than the change in output. So, if we ensure the value of threshold is greater than the maximum change in the output, the maximum change in the consecutive input, like here the change in the consecutive output is 0. Here the change in the consecutive output is, this point is 0.951, and the previous input is 0.587. So, at this point this change is 0.364. Here we have a change of from k equal to 0 to k equal to 1, this change is 0.587. So, in this waveform the maximum change in the input is defined 0.587. So, if we want to avoid the slope overload, we will keep the value of threshold is just greater than, or we will keep the value of threshold equivalent to the maximum change in the consecutive inputs. So, we will keep threshold is greater than equal to 0.587. This is the one method to avoid the slope overload, that we will increase the value of threshold. Now, there is another method. If we increase the sampling frequency, here I am taking 5 samples in 1/2 cycle. If we take 10 samples in 1/2 cycle, so if this is the first input, the next input will be at 18 degree. The next sample will be at 18 degree instead of 36 degree. Then the maximum change in the consecutive input will be reduced. So, in this case we can reduce the value of threshold. So, this is the topic. At this concept 2 or 3 questions have been asked in GATE. So, we will take different graphs. Here we have taken sinusoidal signal. We will take 1 or 2 graphs, and for that we will try to find out the optimum value of, or the value of threshold for which the slope overload can be avoided. Suppose for a certain sinusoidal signal, it can be defined as AM sin 2 pi FM t, or AM sin M is for modulating signal, sin omega mt, and we have sampled this signal at certain sampling frequency. This is Fs. So, at each interval Ts equal to 1 by Fs, at each interval of Ts we will have one sample. These two interval will be, if the frequency is Fs, these two interval will be Ts. So, if we increase the frequency, the interval between the consecutive input to the delta modulator will be lesser. If this interval is lesser, the difference between the consecutive input, this will be lesser. Now, whatever is the value of interval, this interval will always be fixed. So, if the x axis is fixed, the maximum change in the consecutive output will occur at the same point where the graph has maximum slope. Suppose here the graph has approximately 0 slope and this interval is fixed. So, here we will have least difference between the consecutive inputs, where if we compare at these 2 points, again we have fixed interval, but at this point slope is maximum. So, here we have maximum change in the consecutive input, or the change in consecutive input will be slope into the interval is fixed Ts, the sampling interval. So, if slope is maximum, we will have maximum change in the input sequence, the consecutive inputs, and to avoid slope overload, the threshold must be equivalent to the maximum change or just greater than the maximum change in the consecutive inputs. So, E must be greater than delta y max, or we can say that E must be greater than delta y max is equal to maximum value of slope into Ts. For a sinusoidal signal, the maximum slope occurs when the sinusoidal signal is crossing the 0 line at this point, and at this point the slope of a sinusoidal signal, a sine wave, is maximum. Or if we have this signal AM sin omega t, we will say that the threshold must be greater than delta y max, or E must be greater than maximum slope M max into Ts. Now, to get the maximum slope, we will differentiate it. If you differentiate it, we will get amplitude into frequency. This is not maximum frequency, it seems Wm, you can take it as, you may take it as maximum frequency, that is why I am erasing it. This is just omega. Am amplitude of modulating signal, or simply amplitude a omega cos omega t. Now, this is the slope, and maximum value of cos omega t is equal to 1. So, the maximum slope will be a omega. So, E must be greater than a omega into T s, or E must be greater than a omega. T s can be written as 1 by F s, that is sampling frequency F s, or E F s must be greater than a omega. So, if sampling frequency is high, we may take a lower value of threshold. These are the samples input sequence to a delta modulator, and here the slope is maximum. This is one sample and this is another sample. This is another sample. Now, here the slope is maximum, or if we take the previous sample. So, in this region the slope is maximum. So, the change in consecutive input will be maximum here. So, this length I am taking as the value of threshold. Now, at this point what will be the output? We will compare present input with the, or we will initially we will assume y 0 equal to 0. At this point input is greater than, the input is greater than the previous output, sorry, input is positive and the initial output is 0. So, the present input is greater than output. So, the threshold will be added to the output, and threshold is equal to this much length, threshold is equal to this much length. So, the next output will be this one, it is same. Now, again if we compare next input and the previous output, the previous output input is greater than. So, to get the next output we will add the threshold value, and this is the length of threshold value. So, this will be the output. For getting the next, for obtaining the next output, we will compare the next input and this output. Now, the input is less than the, it is clear from the graph, the input is greater than the, input is less than the previous output. So, at next step we will subtract. So, this is the next output. Now, these are comparable. Let us say the input is higher than output, this is the output, and input is higher than output. So, at this interval we will again add. Here input is less than, so we will subtract. Again input is less than, we will again subtract. Again input is lesser, again subtract here. So, this way we will have tracking. So, here I have taken 1, 2, 3, 4, 5 sample in 1/2 cycle. Now, if I take more samples, suppose if I take 10 samples for the same graph, this case we are taking a higher sampling frequency, and we will take, if the sampling frequency is high, we will take 10 samples. This is the first, second, third and 10. Now, and this will be the previous sample to 0. Now, this is the maximum change in output. So, this length we will set as threshold, and the initial output, to start the graph I am assuming initial output as 0, and this is the first input sample. So, at this point we will have this output. At this instant we will have this output, because the second change in input will be less than the first change in input, but the threshold is equal to first change in input. So, the at second step the output will exceed the second input. At this point we will have this output now we will have this kind of output. We have already done it 2 or 3 times. So, I think now you can draw it very quickly, this kind of output 4, 5, 6 and 10 is uniform in terms of x axis, not in terms of y axis, because the sampling frequency is fixed. So, here we will have this kind of graph, this kind of graph will have. Now, if we compare, the graph in black is the expected output. This signal, this was to be transmitted, and the graph in red is the output of delta modulator, and same is in the first graph, but this is for lower value of sampling frequency. So, if the sampling frequency is high, we will have freedom to take a lower value of threshold, and if we take lower value of threshold, that if you can see from the graph, the tracking is better here if we compare from the first graph. But so, it is better to take very high value of sampling frequency. If we again double the sampling frequency, the tracking will be very good, but if you increase the sampling frequency, we have already done it before. What will happen if we increase the sampling frequency? This is analog signal, and if we sample it at a very high frequency, so in 1 second we are calculating bit rate. In 1 second we will have Fs sample, and the quantizer in case of delta modulation, this is 1 bit quantizer. So, each sample will be encoded with 1 bit. So, we will have Fs bit per second. Suppose the sampling frequency is 10 kilohertz. Suppose the modulating signal has frequency of 1 kilohertz and sampling frequency is 10 kilohertz. So, we will get 10,000 samples in 1 second, and each sample is encoded with 1 bit in case of delta modulator. So, we will get in 1 second 10,000 bits. So, we will say we will have 10 kbps bit rate. So, the RV is 10 kbps, and to transmit this signal of bit rate 10 kbps, we need a bandwidth of Rp by 2 hertz on the channel. So, if the sampling frequency is high, bit rate will be very high, then the bandwidth requirement will be high. If the bandwidth requirement is high, so the cost will be higher. So, if we want better tracking, the cost will be higher. So, cost is minimized, compromising little bit of error. So, cost and error is now optimized.